Hello and welcome. In this video, we're going to be taking a look at the chain rule. And of course, we've heard that term before, and we've seen the chain rule for single variable calculus. But here in multivariate calculus, well, we have functions of multiple variables. So we might have a function in terms of x and y, or maybe x, y, and z, or many variables. And we're going to be thinking about those variables maybe depending on some independent variable, such as t, for instance. Maybe x, y, and z are all changing with respect to t. How does the function f, depending on x, y, and z, also change with respect to t? And there's our multivariable calculus chain rule. Let's take a look and start off with the single variable calculus chain rule, where here we might have a function inside another function, like f of g of x. We want to take the derivative with respect to x. Well, we take the derivative of f with respect to g, and then we multiply it by the derivative of g with respect to x. Now, of course, in Leibniz notation, that's a little different. We might think about y being a quantity that depends on u, and u is a quantity that depends on x. So if we were to multiply the rate of change of y with respect to u and the rate of change of u with respect to x, then we can get the rate of change of y with respect to x. That's kind of the similar process that we're going to be looking at here. We're going to start off now by changing f so that it's a multivariable function and not a single variable function. And there's a few different cases we may want to consider. Let's start off with a case where f is a multivariable function and it's a function of multiple single variable functions. As an example, we could say that maybe f is a function of x and y, but x and y are quantities that are dependent on t. So we can treat x as a function, x of t, and we can treat y as a function, y of t. You can kind of see the different layers. F depends on x and y both depend on t. Well, we want to figure out how do we take the derivative of that function, but with respect to t rather than with respect to x or y. Well, you can kind of imagine it's going to be very similar to our chain rule from single variable calculus. We're going to start off with the derivative of f with respect to x evaluated at x and y of t, and then we multiply by the derivative of x with respect to t. In this case, that would be x prime of t. Here, because x is a single variable function, we can use our good old x prime notation from single variable calculus. And we're going to do the exact same thing with our second variable. We're going to be taking a look at the derivative of f with respect to y, evaluated at x and y of t, and we have to make sure we multiply by the rate of change of y with respect to t. So as you can see, t is affecting x and y are each affecting f, so we have to consider both branches here. F depends on x as one branch, f depends on y as another branch, and both of those are changing with respect to t. A great way to represent this kind of chain is using what we call a tree diagram. Sometimes it helps to say maybe z is a quantity that depends on x and y. We can write z is a function of x and y, and x and y are quantities that depend on t, so they are functions as well. X is some maybe function g of t, and y is some function h of t, for instance. Then in our tree diagram, we have z sort of at our top level here. And that will depend on two quantities. We have x and we have y. But each of those quantities, x and y, are also dependent on something else. So we can go into the branch deeper. X is dependent on t, and so is y. Now, on every level of one of those branches, we can take a look at a rate of change. Since z is a function of two variables, we can look at the partial derivative of z with respect to x, and we can look at the partial derivative of z with respect to y. But since x is only a single variable function, then in that case, we are going to be looking at the ordinary derivative of x with respect to t, and same thing with y, dy by dt. In that case, if we want to use Leibniz notation, then dz by dt is the partial derivative del z by del x times dx by dt, plus another partial derivative del z by del y times dy by dt. And here, dz by dt is an ordinary derivative because in the end, we can really just translate this into some expression of just t alone if we want to. Now we can continue to extend this chain rule here, because in this case we have f as a function of multiple single variable functions. But of course, we could have a function that is of multiple variable functions, a function of multivariate functions. Let's take a look at what would happen in that sort of circumstance. In example 2, let's take a look at a function f, which is a function of multiple multivariable functions. For instance, we could have a function f that depends on x and y, but maybe x and y are dependent on s and t. So we can treat f actually as a function of s and t as well if we want. Maybe we would like to figure out what the partial derivative of f is with respect to one of those independent variables, let's say s. If we wish to find this derivative, it's a very similar process. We're going to start off with looking at the derivative of f with respect to x, evaluated at x and y of s and t, and then we take the derivative of the inside function, the derivative of x with respect to s. But here, that would be a partial derivative as well. And then we'll repeat this again by looking at the partial derivative of f with respect to y and the partial derivative of y with respect to s. And we can draw a tree diagram for this as well. If we wanted to think about the quantity z being dependent on x and y, the quantity x being dependent on s and t, and the quantity y being dependent on s and t, then we can draw our branches. In this case, z has two branches, off to x on the left and off to y on the right. X and y each have two branches, one for s and one for t. And so if we wish to take a look at finding the partial derivative of z with respect to s, then we have to consider going down the left-hand branch through x and to s that direction, as well as the right-hand branch, looking at the rate of change of z with respect to y and the rate of change of y with respect to s. What this means is the partial derivative of z with respect to s is going to be equal to the partial derivative of z with respect to x first, and then we have a partial derivative of x with respect to s, and then we have the partial derivative of z with respect to y times the partial derivative of y with respect to s. And it would be a very similar formula if we wanted to find the partial derivative of z with respect to t. But all of these derivatives are partial derivatives because everything we're taking a look at is a multivariable function. Now, when in doubt, just draw a tree diagram like this. Take a look at all the different branches of dependency. One quantity being dependent on several quantities, and each of those quantities being dependent on one or more other quantities. And then you can see which branches you need to take and which rates of change need to be multiplied together and then added to find the overall rate of change of the top quantity with respect to one of the lower branches. Let's take a look at an example. Let's say that we have z as a function of x and y. Z equals sine of x squared plus y squared, where let's say x is equal to r cosine theta and y equals r sine theta. Those are our conversion formulas from polar coordinates to Cartesian coordinates. But what if we want to find out how z changes with respect to r, the distance away from the origin, and how z changes with respect to theta, the angle from the positive x-axis? Well, first of all, I would suggest drawing a tree diagram. Here we have z depending on x and y are both functions of r and theta. From the chain rule then, we're going to be looking at the partial derivative of z with respect to r first by going through z, x, and then r, and also z, then y, then r. And that gives us our chain rule formula. Del z by del r equals del z by del x by del r, plus del z by del y by del r. And at this point in time, we can go ahead and take a look at the functions given and just calculate those partial derivatives. For del z by del r, we'll start off with partial derivative of z with respect to x. That's just going to be a small regular chain rule there. The derivative of sine will be cosine x squared plus y squared times the derivative of the inside, which is 2x. That's just our classic chain rule that we're probably already familiar with from single variable calculus. And then we still have to multiply by the rate of change of x with respect to r. And here we're going to be treating cosine theta as a constant. So the rate of change of x with respect to r is simply just cosine theta. And now let's take a look at the rate of change of z with respect to y. And it's going to be very, very similar. the chain rule again. The derivative of sine will be cosine. We'll leave our x squared plus y squared, and then multiply by the derivative of the inside, 2y, our classic chain rule. And then looking at y as a function of r and theta, but treating theta as a constant, that's just going to end up becoming the partial derivative of y with respect to r is sine theta. Now keep in mind that right now we actually have this expressed del z by del r in terms of x's, y's, and thetas. Potentially you could even have r's in there if you had different functions. However, if you really wanted to, you could always just plug in our formulas for x and y in terms of r's and thetas and plug those in. You could express this partial derivative just in terms of r and theta if you wanted to. Now it's time to look at the partial derivative of z with respect to theta. We'll have to go through z first and then to theta, and then we'll consider the rate of change of z with respect to y and then through theta that direction. That gives us our chain rule formula. Del z by del theta equals del z by del x by del theta, plus del z by del y by del theta. And we've already got several of these derivatives already calculated. We know that the partial derivative of z with respect to x is cosine of x squared plus y squared times 2x. But this time around, we're going to be taking a look at del x by del theta. Looking at x equal r cosine theta, we're going to be treating r as our constant, taking the derivative of cosine theta now. So that's going to give us negative sine theta times r, or just negative r sine theta. And then once again, we have the partial derivative of z with respect to y. That hasn't changed since we calculated that same thing in del z by del r. But this time around, we're going to be taking the partial derivative of y with respect to theta, treating r as a constant. And that's going to get us del y by del theta equals r cosine theta. And once again, if you're interested in maybe simplifying this, you could try plugging in your formulas for r cosine theta and r sine theta for x and y. Plug all of that in and simplify, and you might be able to get a better expression out of this. But this is essentially what you get when you just apply the multivariable chain rule as is without simplifying. Now, what about if you were to take a look at a second order partial derivative? With the multivariable chain rule, we have to maybe use that tree diagram all over again to come up with expressions for the second partial derivative. To give you an example of a second order partial derivative using the multivariable chain rule, let's keep it sort of similar to what we've already looked at in the case where maybe z depends on x and y both depend on s and t. What if we wanted to calculate the second order partial derivative del squared z by del s squared? This is taking the partial derivative with respect to s twice in a row. Well, we do know that if we take the first order partial derivative del z by del s, that's going to be del z by del x by del s plus del z by del y by del s. And now we have to go ahead and take the partial derivative with respect to s once again. Now, to this point in time, you have to remember that the partial derivative of z with respect to x is going to have some x's and y's potentially still in it. And we're going to have to apply the multivariable chain rule all over again. Del z by del x is going to depend on x and y depend on s and t. And even our del z by del y isn't safe. That's going to also potentially depend on x's and y's, and each of those depend on s's and t's. Not only that, but you can see we also have a product rule twice in a row here. We're going to have to take a look at applying the product rule as well as this multivariable chain rule. So let's start off with this first product rule, taking the derivative of del z by del x by del s, all with respect to s. We'll start by leaving del z by del x alone, and then taking the derivative of del x by del s with respect to s again. And then we're going to leave del x by del s alone and take the derivative of del z by del x with respect to s. And here is where we're going to have to apply that multivariable chain rule again. Now, for our second product is going to be very, very similar. We're going to be treating del z by del y as just sort of like a constant here and taking the derivative of del y by del s with respect to s again. And then we're going to be taking a look at leaving del y by del s alone and taking the partial derivative of del z by del y with respect to s. And here is going to be another application of the multivariable chain rule. So we've got our product rules out of the way, but now we just have to go ahead and finish off some more of these partial derivatives. This first term is not too bad. Taking the second derivative of x with respect to s, we can just express that as del squared x by del s squared. And here we're ready to apply that multivariable chain rule. We're going to have to go look through two branches. We're going to take our partial derivative del z by del x, take the partial derivative with respect to x again, and then multiply by del x del s as our first branch. That's where we get this del squared z by del x squared, del x by del s. Now we're going to be taking a look at del z by del x, taking the partial derivative with respect to y, and then take the partial derivative del y by del s. Be careful about the order of partial derivatives in this notation. We started off with the derivative del z by del x, and if we differentiate with respect to y, then in the denominator we have del y del x, in the numerator del squared z. And here's our del y by del s. There's our first of two chain rules that we have to do. Our next term, we're simply just taking the partial derivative of del y by del s with respect to s again. And that's going to be del squared y by del s squared. And then we have to look at this multivariable chain rule for our last term. Taking a look at differentiating del z by del y with respect to s means we need to take del z by del y, look at the partial derivative with respect to x, and then take a look at the derivative of x with respect to s. And then our second branch, take the del z by del y, partial differentiate with respect to y, and then multiply by del y by del s. Once again, be careful of the order of these partial derivatives. We start off with del z by del y, and in the first branch, we then differentiate with respect to x. So we have del x del y in the denominator, and then del x by del s. And on the right-hand side of this multivariable chain rule, we have del squared z by del y squared. That's taking del z by del y, and then looking at the second partial derivative with respect to y a second time, multiplied by del y by del s. So as you can see, this second partial derivative, if you have to apply the multivariable chain rule a second time, it's also going to throw product rules in there too. It can become quite a mess. So here is just the benefit of drawing those tree diagrams. Without those, it's pretty hard to just try to memorize this whole form. It would be pretty useless to just memorize it. It's better off to just think about which branches you have to go down that tree diagram in order to reach the variable of choice. In this case, we're looking at with respect to s. Now, other than making some very complicated looking partial derivative formulas, this multivariable chain rule actually opens the door to simplifying many problems we've seen before. As a very classic topic in single variable calculus, we looked at related rates. And here, related rates, when we start taking a look at multivariable functions, really won't be so bad. Let's take a look at kind of a geometry problem where maybe we have a rectangular box full of water. And the volume of water in that box is a pretty easy formula. It's just simply going to be length times width times height. And in single variable calculus, we're often just trying to see how the rates of change of each of these quantities are related together, assuming that they are all dependent on t. Why don't we maybe just assume that volume here, of course, is dependent on three variables, length, width, and height. And let's say that length is changing with respect to time, width is changing with respect to time, and height is changing with respect to time. If we want to see how volume changes with respect to time, given some rates of change of length, width, and height, then we can just go ahead and use this multivariable chain rule to state our rate of change of volume. Going down each of the branches here, we can see that dv by dt is equal to del v by del L, dl by dt, plus del v by del w, dw by dt, plus del v by del h, dh by dt. And right away, these three partial derivatives, del v by del L, del v by del w, and del w by del h, are very quick to calculate, seeing as how we're just going to be treating two of the variables as constants. That gives us dv by dt equals wh dl by dt plus lh dw by dt plus lw dh by dt. Now, with those related rates, we can go ahead and plug some values into this problem. Let's suppose that we have the width increasing at 2 centimeters per minute, and the length is decreasing at 1 centimeter per minute, but we're pouring water in at the same time with a rate of 1 liter per minute. If that's the case, it's maybe a little difficult to figure out whether the height of water is going to be increasing or decreasing. Let's assume that currently the width is 20 centimeters, length is 40 centimeters, and there's currently 8 liters of water in the tank. Well, we can plug in most of these values if we like. We know, of course, that W is currently 20 centimeters, and the rate of change of W with respect to time is 2. It's increasing, so that would be positive. We're also, in this problem, given the current length, but since length is decreasing, we'll say that its rate of change is negative, decreasing at 1 centimeter per minute. As far as volume, we just have to do a quick conversion from liters into cubic centimeters so that all of the units match up properly. 1 liter is 1,000 cubic centimeters, so the current volume is 8,000 cubic centimeters, and the rate of change of volume with respect to time is 1,000 cubic centimeters per minute. Now, you can see based off this formula that we also need to know what the current value of H is in order to find out what dH by dt is, the rate of change of the depth of water. If you go ahead and plug in 8,000 for our current volume, 20 centimeters for our current width, and 40 centimeters for our current length into our classic formula V equals LWH, then we can at least solve for H and get a height or depth of water of 10 centimeters. Now it just involves a little bit of algebra to go ahead and solve for dH by dt. You should end up finding that we end up with dH by dt equal to 3/4. And since that's positive, that tells us that the depth of water is increasing at 3/4 of a centimeter per minute. Now, another great application of our multivariable chain rule is actually to kind of put aside our classic method of implicit differentiation and replace it with a potentially more clever and convenient form of finding derivatives. Here is where we're going to be looking at an equation that relates, let's say, x, y, and z. But we're treating z as dependent on x and y. If it's not given in the form of a function, then typically we have to take the derivative of both sides of the equation and pay close attention to what we're treating as an independent variable and what we're treating as a dependent variable. But let's take a look at a different strategy here. If we want to start off with a classic example of implicit differentiation in a class of single variable calculus, you may have seen this folium of Descartes before, and this would be the equation x cubed plus y cubed equals 6xy as an example. It's an interesting looking curve if you were to graph it, but it's definitely not a function, and it doesn't pass the vertical line test. However, we can always still take a look at slope of a tangent line on a curve by finding an expression for dy by dx. Typically, what we would do is take the derivative of both sides with respect to x, and whenever we see terms involving y, we have to apply a little single variable chain rule. And don't forget to have a little dy by dx factor in the derivative. Instead, what I might suggest now is to move the equation around and set one side equal, let's say, to 0 conveniently. From there, we can treat the whole left-hand side of this equation as being a function of two variables. Why don't we maybe choose capital F here just to indicate that something's a little different than our typical lowercase f for single variable functions. Now, if we want to try using the chain rule on this, let's say we want to find the derivative of f of xy with respect to x. By the chain rule, the derivative with respect to x of f of x comma y is going to be the partial derivative of f with respect to x at xy, but of course the derivative of x with respect to x is just 1, plus the partial derivative of f with respect to y at xy multiplied by the derivative of y with respect to x. But since our function f of x comma y equals 0, then the derivative must also equal to 0. And that means that we can take the right-hand side of this chain rule expression and set that equal to 0. If we want to use shorthand notation, we might just say that f partial x plus f partial y times dy by dx equals 0. Well, in this particular problem, we're really trying to find an expression for dy by dx. And we can rearrange this equation to get dy by dx equals negative f partial x, if we move that to the other side, and then divide by f partial y. This formula here can be an absolute lifesaver. It's very easy to treat y as a constant and just take the derivative with respect to x to get f partial x. And it's very easy to treat x as a constant and take the derivative with respect to y to get f partial y. And then we just simply need to form a fraction, slap a negative sign in front, and we've got an expression for dy by dx. In this example, if we're going to be taking a look at f partial x, treating y as a constant, then the derivative of x cubed is going to be 3x squared. The derivative of y cubed is going to be 0, and the derivative of negative 6xy with respect to x is going to be minus 6y. Then in the denominator, we just look at treating x as a constant and take the derivative with respect to y. The partial derivative of x cubed with respect to y will be 0. The partial derivative of y cubed with respect to y will be 3y squared. And then the partial derivative of negative 6xy with respect to y is going to be negative 6x. Don't forget that negative sign in front. There we go. There's an expression for dy by dx without having to do a whole bunch of extra algebra after applying the differentiation operator to both sides of the original equation. This really allows us to do all of the algebra up front and just do two partial derivatives and form a fraction. Now the good news is we can continue to use this technique even when we have equations of 3 or more variables. Let's suppose we have some equation involving 3 quantities, x, y, and z. E to the z sine y plus x squared equals 3z. If we want to treat z as being dependent on x and y, we might want to find expressions for the rate of change of z with respect to x and y, treating the other variable as constants. Well, we can do something very, very similar here. We'll start by rearranging that equation and moving our terms to one side. That leaves us with equal to 0 on the other side. Then we're going to let f be a function of 3 variables. We'll just treat this whole left-hand side as some function capital F of x, y, and z. Now, since we're taking a look at the partial derivatives of z with respect to x and z with respect to y, we're going to differentiate this function with respect to x and y. Using the chain rule, the partial derivative with respect to x of this function is going to be f partial x plus f partial z del z by del x. If you want to make a little bit of sense as to how we get this chain rule, perhaps a tree diagram is better. We have a function of 3 variables, x, y, and z. So we'll have 3 branches below that, x, y, and z. X and y are independent variables. We're going to then look at z as being a function of x and y, and there are only 2 branches that we have to consider here. There's our 2 branches. Once again, since our function f of x, y, z is equal to 0, then this derivative must be equal to 0, and we can rearrange to get an expression for del z by del x. This tells us that del z by del x equals negative f partial x over f partial z. And we can go and quickly compute those 2 things. In this example, f partial x is just going to be treating y's and z's all as constants. So the derivative of this first term with respect to x is just 0. The derivative of x squared with respect to x is 2x. And then the partial derivative of negative 3z with respect to x, treating z as a constant, is 0. So that's all we have in the numerator. And then in the denominator, we're going to be taking a look at the partial derivative with respect to z, treating x and y as constants. So we won't have to worry about this middle term here. The partial derivative of e to the z sine y, treating sine y as a constant, is going to be e to the z sine y. And then the partial derivative of negative 3z with respect to z is just going to be negative 3. Don't forget the minus sign in front. Now, what about if we wanted to find the partial derivative of z with respect to y? Well, we have the tree diagram handy here already. We're going to be taking a look at two branches. The partial derivative of f with respect to y, and the partial derivative of f with respect to z, and then the partial derivative of z with respect to y. That gives us our next multivariable chain rule. This function of x, y, z equals 0, so this overall derivative must be equal to 0, and we can rearrange to get an expression for del z by del y without using implicit differentiation. You can see a kind of a nice pattern here. This is just going to be negative f partial y over f partial z. If we want to calculate del z by del y for this function, then we've already got a little bit of a head start. We've already got a particular expression for f partial z. That was e to the z sine y minus 3. We just need to figure out what f partial y is. And be careful, here we're going to be treating z and x as constants. So e to the z is a constant, and we just need to take a look at the derivative of sine y, which is going to be cosine y. The partial derivative of the other two terms are both 0 since x's and z's are treated as constants. All of these partial derivatives here are now being calculated without having to use classic implicit differentiation and all the algebra that goes along with it. So hopefully you find those applications are possibly some of the best ways to see where the multivariable chain rule makes life actually easier. Looking at the second order partial derivative just involving the chain rules on its own is a pretty complicated looking formula. But in reality, this chain rule is very helpful for finding ways to get around some of our typical stumbling blocks from previous sections, especially that implicit differentiation application. That's what I'll suggest using pretty much from now on anytime that you have an equation relating multiple quantities that can't be expressed as a function. Now, we're going to be seeing other uses of the multivariable chain rule coming up in future videos, so stay tuned. Thanks for watching, and I'll see you in the next video.